The precise spray of fuel that would revolutionize internal combustion engines forever misted into the intake manifold of the Chevrolet Corvette on March 15, 1957. Zora Arkus-Duntov, Chevrolet's chief engineer, watched as the Rochester Ramjet fuel injection system delivered exactly the right amount of gasoline to each cylinder with mechanical precision that no carburetor could match. "Gentlemen, we've just eliminated fuel starvation, flooding, and altitude problems," Arkus-Duntov announced to his engineering team, as the 283 cubic-inch V8 produced a remarkable 283 horsepower. 1 horsepower per cubic inch, a milestone that had seemed impossible with carburetor technology. "Every cylinder is now receiving precisely the fuel it needs, exactly when it needs it." Chevrolet's Rochester Ramjet fuel injection represented the first successful attempt to bring aircraft-grade fuel metering technology to mass-production automobiles, solving fundamental problems that had limited engine efficiency and performance since the invention of the internal combustion engine. The engineering achievement was revolutionary. Chevrolet had figured out how to mechanically calculate and deliver optimal fuel quantities to individual cylinders under all operating conditions, creating engines that ran cleaner, more efficiently, and more powerfully than anything achievable with traditional carburation. What started as racing technology for Indianapolis 500 competitors would eventually become standard equipment on virtually every automobile engine, fundamentally changing how internal combustion engines operate and perform. If you love discovering the untold stories behind automotive history's most incredible innovations, please like this video and subscribe to the Car Chronicles. Early 1900s to 1950s, the carburetor limitation. For the first 50 years of automotive history, internal combustion engines relied on carburetors to mix air and fuel in the proper ratios for combustion. Carburetors were mechanical devices that used engine vacuum and airflow to draw fuel from a reservoir and atomize it for mixing with incoming air. While carburetors were relatively simple and inexpensive, they suffered from fundamental limitations that restricted engine performance and efficiency. Carburetors could not precisely control fuel delivery to individual cylinders, often resulting in some cylinders running rich while others ran lean, reducing overall engine efficiency. Carburetors were compromised devices that worked adequately under ideal conditions but struggled with variations in altitude, temperature, acceleration, and load, explained automotive engineer Charles Kettering. They were inherently imprecise, delivering approximate fuel mixtures rather than optimal ones. The problems were particularly evident in high-performance applications. Racing engines suffered from fuel starvation during hard acceleration, flooding during cold starts, and inconsistent power delivery under varying conditions. Aircraft engines had already moved to fuel injection to solve these problems. But automotive applications presented different challenges. Altitude changes created additional complications for carbureted engines. As vehicles climbed to higher elevations, reduced air density caused carburetors to deliver overly rich fuel mixtures, reducing power and increasing emissions. Descending to lower altitudes had the opposite effect, creating lean conditions that could damage engines. Cold weather starting was another persistent problem. Carburetors required manual choke adjustments to provide rich mixtures for cold starts, and inexperienced drivers often flooded engines or failed to provide adequate enrichment for reliable starting. 1940s to 1955. Racing development. The development of automotive fuel injection began in racing applications, where the performance limitations of carburetors were most apparent. Indianapolis 500 race cars in the late 1940s began experimenting with mechanical fuel injection systems adapted from aircraft technology. The Hilborn fuel injection system, developed by Stuart Hilborn in the early 1950s, became the gold standard for racing fuel injection. Hilborn's mechanical system used engine-driven pumps and precision metering to deliver fuel directly to intake ports, eliminating the air-fuel mixing inconsistencies that plagued carburetor systems. Racing results were dramatic. Fuel-injected race cars produced more power, achieved better fuel economy, and ran more consistently than carbureted competitors. The technology allowed race engines to maintain optimal air-fuel ratios regardless of track conditions, altitude, or weather. Fuel injection gave us power and reliability that carburetors simply couldn't match, recalled Indianapolis 500 mechanic George Salih. We could tune each cylinder individually and maintain precise fuel delivery under the extreme conditions of racing. The success of racing fuel injection attracted attention from automotive manufacturers, who recognized the technology's potential for production vehicles. However, adapting racing fuel injection for mass production required solving significant cost and complexity challenges. General Motors began serious fuel injection development in 1952, working with Rochester Products to create a system that could be manufactured affordably while providing the precision and reliability necessary for consumer vehicles. 1955–1956, the engineering challenge. General Motors' fuel injection development team, led by John Dolza and Harry Barr, faced the enormous challenge of creating a fuel injection system that could be mass-produced at reasonable cost while delivering the precision and reliability that consumers expected. The fundamental engineering problem was creating a mechanical system that could calculate optimal fuel delivery for constantly changing engine conditions. The system had to respond instantly to throttle changes, automatically adjust for temperature variations, and maintain precise air-fuel ratios across the entire engine speed range. The Rochester Ramjet system used a sophisticated arrangement of mechanical components to achieve these goals. An engine-driven fuel pump pressurized gasoline to consistent pressure levels, while a fuel manifold distributed pressurized fuel to individual injection nozzles mounted in each intake port. The metering system was ingeniously mechanical. A throttle-operated fuel control unit calculated fuel requirements based on airflow and engine speed, while temperature-sensitive components provided automatic compensation for cold starts and warm-up conditions. The Rochester system was essentially a mechanical computer that solved fuel delivery equations in real time, explained engineer John Dolza. Every component worked together to calculate and deliver precisely the right amount of fuel for existing conditions. The system required no electrical power beyond normal ignition requirements, making it compatible with existing automotive electrical systems. All fuel metering was accomplished through mechanical linkages and hydraulic controls that operated reliably under automotive service conditions. March 15, 1957. The production launch Chevrolet introduced the Rochester Ramjet fuel injection as a $484 option on the 1957 Corvette and select passenger car models. The system was positioned as the ultimate performance option for enthusiasts who demanded maximum power and efficiency from their engines. The results were immediately impressive. The fuel-injected 283 V8 produced 283 horsepower, achieving the coveted 1 horsepower per cubic inch ratio that had been a benchmark for high-performance engines. This power level exceeded anything available with carburetor technology in the same displacement engine. More importantly, the fuel-injected engine delivered consistent performance under all conditions. Cold starts were immediate and reliable. High-altitude operation maintained full power, and acceleration was smooth and predictable across the entire throttle range. The fuel-injected Corvette was like nothing we'd ever driven, recalled automotive journalist Tom McCahill. It started instantly in any weather, ran perfectly at any altitude, and delivered consistent power that carbureted engines simply couldn't match. Customer response was enthusiastic among those who could afford the premium price. The $484 option cost represented a significant investment, but buyers immediately appreciated the superior performance and reliability that fuel injection provided. The automotive press was impressed by the technology's sophistication and effectiveness. Road and Track magazine declared that fuel injection represents the future of automotive engine technology. 1958 to 1965, market challenges. Despite its technical superiority, the Rochester Ramjet fuel injection faced significant market challenges that limited its adoption. The system's premium pricing put it beyond the reach of most consumers, while its mechanical complexity created service challenges for dealership technicians. Service difficulties were particularly problematic. The Rochester system required precise adjustment and calibration that many mechanics weren't trained to perform. Improperly adjusted fuel injection could actually perform worse than carburetors, creating customer satisfaction problems that damaged the technology's reputation. Manufacturing costs remained high throughout the system's production run. The precision components and complex assembly required for reliable fuel injection operation prevented cost reductions that might have expanded market acceptance. Competition from improved carburetor designs also challenged fuel injection adoption. Manufacturers like Carter and Holley developed sophisticated multi-barrel carburetors that delivered much of fuel injection's performance advantage at significantly lower cost and complexity. By 1965, Chevrolet discontinued the Rochester Ramjet system due to slow sales and service complications. Fewer than 2,000 fuel injection systems were produced during the 8-year production run, making them extremely rare and valuable among collectors today. However, the technology had proven that mechanical fuel injection could work reliably in automotive applications, establishing the foundation for future electronic fuel injection development. 1970s, 1980s. Electronic revolution. The revival of automotive fuel injection came through electronic technology that solved the cost and complexity problems that had limited mechanical systems. Electronic fuel injection used computer controls and electrically operated injectors to achieve the precision of mechanical systems with greater reliability and lower manufacturing costs. Bosch led the electronic fuel injection revolution with the D-Jetronic system introduced on European vehicles in 1967. Electronic systems used sensors to monitor engine conditions and computer controls to calculate optimal fuel delivery, eliminating the complex mechanical components that had made earlier systems expensive and difficult to service. The 1973 oil crisis and subsequent emissions regulations accelerated electronic fuel injection adoption. Computer-controlled fuel systems could maintain precise air-fuel ratios necessary for catalytic converter operation, while optimizing fuel economy to meet new efficiency standards. By the 1980s, electronic fuel injection had become standard equipment on most new vehicles. The technology that had begun as an exotic performance option for Corvettes became essential equipment for meeting emissions and fuel economy regulations. Modern fuel injection systems are far more sophisticated than the original Rochester Ramjet, incorporating multiple sensors, computer controls, and advanced injection strategies. However, the fundamental principle remains unchanged: delivering precisely the right amount of fuel to each cylinder at exactly the right time. The legacy and modern impact. The development of automotive fuel injection represents one of the most important engine technology advances in automotive history. By solving the fundamental limitations of carburetor fuel delivery, injection systems enabled the clean, efficient,
powerful engines that defined modern automobiles. The Rochester Ramjet's technical achievements were remarkable for their time and established principles that continue to guide fuel injection design today. The system proved that precise fuel metering could improve power, efficiency, and reliability while reducing emissions.
From a technological perspective, fuel injection represented one of the first successful applications of precision manufacturing and control system technology to mass production automobiles. The engineering lessons learned from mechanical injection development directly influenced the electronic systems that followed. Contemporary direct injection systems are the latest evolution of the technology that Chevrolet pioneered in 1957. Modern engines inject fuel directly into combustion chambers with computer-controlled precision that optimizes power, efficiency, and emissions for every operating condition. The cultural impact of fuel injection extends beyond technical achievements. The technology democratized high performance by making precise engine control accessible to ordinary drivers, not just racing professionals with specialized knowledge. Today, virtually every automobile engine uses fuel injection technology that traces its origins to the Rochester Ramjet system. The mechanical precision that once distinguished exotic performance cars has become standard equipment that drivers take for granted. The fuel injection story reminds us that revolutionary automotive technologies often require decades of development before achieving widespread adoption. Zora Arkus-Duntov's vision of precision fuel control eventually transformed the entire automotive industry, even though initial market acceptance was limited. Modern discussions about engine efficiency and emissions control frequently overlook the historical significance of fuel injection development. The precise fuel control that enables today's clean, efficient engines began with mechanical systems that seemed impossibly complex for their time. If this story moved you, subscribe to the Car Chronicles and hit that like button. Share it with someone who needs to know that the most important automotive innovations are often the ones working invisibly under the hood, making every drive more efficient, powerful, and reliable than previous generations could imagine. What's your favorite fuel injection innovation? Let us know in the comments how precision fuel control has influenced your automotive experiences and engine performance expectations.